Everybody, I want to prove a homework problem from Underwood, Dudley's number theory book. And I'm going to choose to prove what they call the contrapositive. If you take a look at this left-hand side where it says n is congruent to 4 mod 9, we'll call that proposition A. And then proposition B will just be everything to the right of the comma. It says that n cannot be written as the sum of 3 cubes, okay? So this is in a direct, the way it's worded is in this form A implies B. The truth of A implies the veracity of B, okay? I want to prove the contrapositive because I think it's just more straightforward to do it that way. The contrapositive is logically equivalent to the original proposition. That is, you can think of this left-hand side as being not B. The tilde is the logical operator for negation. So not B implies, and this part down here would be not A down here. I couldn't keep it all on one line. Okay, but this right up here, this says A implies B, this says not B implies not A. One way to keep that straight is if it is raining, the ground is wet, but if the ground is not wet, it's not raining. They're logically equivalent, right? Okay. Now another way to write this is you can say that n not congruent to 4 mod n means the very same thing as saying that n is not equal to some multiple of 9, okay? And I'll just write that 9m. That might be a slightly more palatable way to interpret this, okay? So what we do right here is we just go through all the possible cubes reduced mod 9. Okay, now every integer when divided by 9 leaves a remainder of 0, 1, 2, 3, 4, 5, 6, 7, or 8, right? When you divide a number by 9, the remainder can be no bigger than 8 and no less than 0, okay? And so what we're going to do is verify that k cubed, when you cube an integer, it's only going to be congruent to 0, 1, or 8. That is, a cube will only leave a remainder of 0, 1, or 8 when divided by 9, and that's a pretty sparse set of numbers, which makes this computation pretty easy. Now let's go down. The rest of this is just a bunch of computation in modulo 9. I didn't want to write mod 9 over and over, but you can see that 0 cubed is certainly 0, 1 cubed is certainly 1, 2 cubed is 8. Now notice that 3 cubed is 27, but that's a multiple of 9, so it leaves a remainder of 0. And I won't do any of the rest of these. These calculations are fairly direct, but you can see going through all possible remainders, 0 through 8, we only have the fact that a cube can be congruent to 0, 1, or 8, okay? Now we use that truth down here. We just go through all the possibilities. We just go through all the possibilities here. I went through all the possibilities, 0, 1, let's see, oops, that should be, or never mind, I'm sorry. Everything's still good. Notice that when we allow all the cubes to be congruent to 0, we get 0. When we allow all the cubes, we allow 2 of them to be 1, we get 2, and so on. So you see, these are all the possible remainders. Now right here, I didn't finish this part right here. This would be congruent to 1 also, right? 10 is congruent to 1, okay? And then 16 is congruent to 7. 2 times 7 plus 2 is 16, right? And then 24 is congruent to 6. Again, what is that? That would be 2 times 9 plus 6 is 24, right? And so you see, the only thing that gets left out here, we have, let's see, 1 happened here. We have 0, 1, 2, 3, 8, 7, and 6. So the only remainders that were excluded are 4 and 5. I'll put 4 comma 5. Okay. And again, you guys, you can verify this if you want, but the only remainders that I was able to exclude for the sum of 3 cubes would be 4 and 5. And note that all we had to do was prove it for 4. So this original problem could have been 4 or 5, okay, the way I've done it. But again, Underwood Dudley was just interested in showing it wasn't congruent to 4 mod 9. And so it looks like we proved what we set out to prove. Now, something that you may be interested in that I was doing as far as the calculations go, there's a well-known result that if you have an integer, it's always going to be congruent to the sum of its digits, mod, I'll call that SOD, sum of digits mod 9. That's owing to the fact that 10 to the n is congruent to 1 mod 9 for all natural numbers, okay? So this is modulo 9, and this stands for sum of digits. Let me give you a concrete example, because that explains some of these computations that I didn't talk about really. So just a concrete example is consider 392, okay? Consider the integer 392, okay? 392. Now, if you sum those digits, you end up getting 9 plus 2 plus 3 is 14, all right? All right, but notice that both of these values leave a remainder of 5, okay? Let me, you see, that both of these would be congruent to 5. Modulo 9, right? It's clear for 14. Now, 392 is 9 times 43 plus 5, okay? Now, that's a fairly simple computation, but 392 is 9 times 43 plus 5. 9 times 43 is 360 plus 27 is 287 plus 5 is 392, okay? So the 392 is 9 times 43 plus 5. So you see you get this, that's kind of the direct definition of congruence, but see you get these same two remainders. So sometimes congruence arithmetic is thought of as remainder arithmetic, but the sum of digits result is very, very useful for the computations. Notice right here, you just sum the digits rather than saying it the way I said it a while ago. 4 plus 2 is 6, 1 plus 6 is 7. It's really nice. It's a nice congruential reduction tool for modulo 9 arithmetic. But anyway, we have proved what we set out to prove, and even a stronger statement that this is not congruent to 4, which again is what Dudley was looking for in his problem number 19 in his elementary number theory textbook. But I seem to have discovered that he could have also said for 5 as well. So anyway, this is a QED right here. Latin for thus we have demonstrated, quandam est demonstrandum. So let's write that down, QED. And we finish this, and hope you enjoy.